All right, so I passed out a worksheet related to this so you could draw on it yourself, but what we started with was just a picture of this, what's red here. It's not red on your worksheet because I don't have color copying budgets, but this red exact rate of change curve that expresses the rate at which sand was being poured onto a scale, measured where the horizontal axis is in seconds and the vertical axis, the dependent quantity, is measured in hundreds of pounds per second. So we have rates between, looks like on this graph, maybe about like 0.7 to 5, which would be like 75 to 500 or so. I said 0.7, then I said 75, but approximating just visually pounds per second at which the sand is being poured onto the scale. So if I wanted to measure how much sand cumulatively has been placed onto the scale since, well, this time zero, I don't know what time zero is relative to, is it like noon, whatever it is, but time zero is when we then also start measuring this accumulation here, just based on how this was set up. Now on the worksheet there was a whole paragraph about let's do it this way. Let's start at time, there we go. We'll start at time zero and highlight points every 0.3 seconds, starting from 0 until 1.8 seconds. So this is what we did in class on Thursday. So this is scaled differently because for whatever reason I can't get GC to scale appropriately on this computer so that it looks more like this, but it's the same graph. And on here you can maybe see, since there's grid lines, goes from about 0.25 up through almost 5 at the peak, and then goes back down again, meaning sand's being poured on relatively slowly, still rather quick. If you're going at 25 pounds per second, all the way up through nearly 500 pounds per second, and then slowing down again. If we're trying to track how much sand is on the scale at any point in time, I know, well, just based on this rate, not by knowing any other outside, like how much was there at time zero, just what happened because of this rate. Well, I'd start from 0, and then I'd go up from there. So I'd go up relatively slowly at first, and then most quickly around time 1 second, and then slow down again. Now we were doing a specific method of computation, but if I just wanted to like freehand sketch what I thought this would look like, let's see if I can get this guy started. Like not doing any computations, but just thinking about, all right, how would this have to happen? We'd start at 0 because I don't have any, I'm not using any initial values, just solely based on this rate function, what happens since time 0. So, well, at time 0, nothing's happened yet. And then by time 1, I've got the fastest rate, whereas at the beginning, I've got a relatively slow rate of growth, of increase in weight. And then by the end here, by 2.5, it's really slow again. So if I'm measuring the amount of sand on the scale in hundreds of pounds, then it's going to increase from 0, like I don't know what the Y values are, so I'm not really paying attention to these because I'm not doing computations this instant. But growing slowly and then more and more quickly indicates, you know, going up like this. And then once I pass this fastest point, I went up a little high. Make that not quite so steep so quickly here. So that the fastest part is here, and then it slows down again. The weight doesn't decrease, so I'm not going to make this go downhill. What I'm going to do is make it not go uphill so fast, because I'm still pouring sand onto the scale. This is still a positive rate here. It's just a low positive rate. So adding at, you know, the 20 to 30 pounds per second instead of 500 pounds per second like in the middle. So if this is time going on as I go to the right, the height of this graph indicating the weight of the sand increases most quickly, so goes up relative to across more in the center section. So this is a fast increase, slow increase, slow increase. So just this general sort of shape, I hope you can kind of imagine that from the data without doing any computations. But what I asked you to do on this in reality was, let's do some computations. So on this back page here was the kind of the very specific computations. If I want to find a of 1.4 using not like the function notation, which I actually have that shown at the top of this. This is the actual function that highlighted in blue. It's pretty awful looking. Not using that, just thinking about what it looks like in the graph. So eyeballing it and picking out some numbers though, as opposed to just steeper and less steep. The very vague estimation that I did just a moment ago. So looking at this, if I want to find a of 1.4, and I'm using lowercase a, starting value of accumulation as time 0, and using intervals of width 0.3, meaning 0.3 seconds, just like we had on the moving graph a minute ago. We want to know a few questions first just for the setup, and then how to utilize this whole accumulation sum formation that we've talked about now for a while. All these different parts, you've seen questions about it in homework that's due tonight. There'll likely be some more, not the same sorts of questions, but just interpreting parts of this for the iMath quiz that's going to be open all tomorrow, well, from 8 a.m. through midnight. And just make sure you understand the meanings of these pieces for your test. So it's not just like memorize a bunch of letters in order. Make sure you understand what they mean. This is all about using constant rate of change, but in small intervals at a time. So again, the first part represents all the complete delta x width intervals. In this case, it'd be all the complete intervals of width 0.3 between the starting value of x, 0, a, lowercase a, and current value of x, or well, our ending value that we're trying to calculate here is 1.4. So moving picture-wise, just about there accidentally. Let's see. Oh, so I can, there we go. Nope. Touchy. See if I can. Nope. There's 1.4. So I want to know, based on an approximation where, and just dragging these as close as I can, about 0.3, I want to know how high is this? The y value there is the value a of 1.4 as an approximation using, and this is approximate a, not a sub f, not an exact computation, but this approximation using starting value of accumulation at 0 and using that rate function just starting at 0, not worrying about any initial values. Like there was already some stuff on the scale, and intervals of width 0.3. So this isn't exactly that, but that's as close as I could get it. So I want to know, oh, well, how much has accumulated by then? The slow, slightly faster, these two are pretty much the same, but that's actually this third and fourth full interval form this long-looking segment there. They're just very similar rates, so hard to tell one apart from the other in that picture. And then you can tell, oh, well, this shorter part here, that's this section here, that's this current interval that x is in the middle of. It's not a full 0.3 units long if I'm at x equals 1.4, because this last interval would only extend from 1.2 to 1.4. So if I want to know, all right, well, how much accumulates due to those 4 full intervals and this 0.2 extra of x at a 5th rate, I'm sure you can do this, grab a calculator or something, say, all right, so this value times whatever it's like this, 0.3, this value times 0.3, this value times 0.3, this value times 0.3, and then this last one times 0.2. But what I want to take a look at is how this all relates to all the mysterious letters and symbols in our summation, just to make sure that they have a meaning and they're not just mysterious letters and symbols. So back to this. So how many complete intervals did we have between 0 and 1.4? How many full-length 0.3 intervals were there? 4, right? That's that x minus a over delta x floor. If you wanted to compute that, we could do it the hard way, but since it is maybe easy numbers, and you could see it in a picture. There's 4 full intervals, but that's 1.4 minus 0 over delta x was 0.3, and then rounded down. So that'd be how, computer doing this sort of thing would calculate this. It doesn't just look at a picture and say, oh, there's 4 line segments. This computation is where we get that 4 from. So looking at the chart below, there's column headings that are each pieces of this, kind of order of operations wise. The first one starts kind of inside, and then it goes out farther and adds more pieces for a while. Let's see. Let me scroll this guy. So complete intervals. So this J, first interval, second interval. If I wanted to fill this out, I'd have 2 more rows of this chart to fill out. Third interval and fourth interval. So J, although it's just an index to the sum, we set it up so that it's not only just an index, something to substitute in. It also will have, when I substitute in j equals 1, that tells me something about the first interval. When I substitute in j equals 2, it tells me something about the second interval. So this j is the interval number that we're talking about. However, in order to get that to work, notice that it's j minus 1 that shows up in all these expressions. J minus 1, j minus 1. So j is an interval number, but when I substitute in j equals 3, I don't end up seeing 3s, I end up seeing 2s. Well, not a bunch of them. There's only one of them. This is the inner expression from our sum that then we take the approximate rate function, evaluate it there, and then we take that rate value and multiply it by delta x. So these 3 things in sequence, this would be the kind of order of operations if you're doing this manually. This gives us what? What is this a plus something delta x? All of those, regardless of the value of j, because j is going to have a bunch of different values. What sort of thing are these? So if j equals 1, I get a. If j equals 2, I get a plus delta x. 1 delta x, that is. If j is 3, I get a plus 2 delta x. What are these? Are these rates? Are they amounts of sand? Are they time? Are they, what are they? Yeah, they're different x values. They're going to be put into the rate function. I mean, just out of context, this could be literally anything. But the way that this shows up in our whole summation, it's a sum of, I'll just recopy it down here, r of a plus j minus 1 delta x times an additional delta x plus some other stuff, where this sum is found by adding up its values when j goes from 1 through, well, however many complete intervals we have. So this a plus j minus 1 delta x is used in the sum as the places where we evaluate the approximate rate function. Or, like I said, since it's only actually at the left end of intervals, it could be r sub f also. It could also be places where we evaluate our exact rate function. Because at the left end of intervals, the ways that we've constructed this, those have the same value. That's where the horizontal line segments meet the curve. So those two, the curves and the line segments, have the same values at x equals a, x equals a plus delta x equals a plus 2 delta x, and so forth. Because that's how we made this approximate rate function. So these are all x values. And they're all at the left end of intervals. So this is the x value at a through a plus delta x. And then the next interval is a plus delta x through a plus 2 delta x. And then a plus 2 delta x through a plus 3, and so forth and so forth. So each is the same width. It begins at this x value and ends at, well, where the next interval starts. So these are the x values. So these are the rates. rates from the approximate rate function, but they're also exact rate values as well. Yeah.
Talking about left sides,
Mm-hmm.
the function that we're talking about this from is just a little above what we're looking at right
Right.
now. Can you scroll up a little just so I
The writing's going to stay where it is, but
Yeah, thank you. It says in the second half of the function rx times x minus left x.
mm-hmm.
I mean, I might have missed something, but what is it trying to say here? Because I thought that it should be rate of left of x, beginning of the continuation.
Which will also be the same. So that's the same. So this could be r of x. This could be r of left of x. It could be r sub f of left of x. All of those would have the exact same value in that spot. So all of those mean the same thing. So r of x would have to be separately defined, but we defined it in a paragraph. We didn't write out the function. But this r of x is that piecewise constant function. So its value at, in this case, it would be at 1.4, is the value at the left end of the interval, but it stays the same throughout. So there's like 3 different ways we could write this rate here that would all be equivalent. This r of x, r sub f of left of x, or r of left of x. The only thing we wouldn't want to write here that sounds kind of similar is r sub f of x, because r sub f of x is the curve, and as x is at 1.4, that would be that lower value where the red curve was at by time 1.4. But the rest of those other 3 would all have the exact same value. Thank you. Let's see if I can line this back up again. There we go. All right, so again, these are just the a plus something. Those are just x values. That's the input to the rate function. The rate function takes x values times as its input. So the values of these, because we're actually supposed to be doing some numerical approximations with this, would be 0, 0.3, 0.6, and 0.9. The next position would be 1.2. That's not the beginning of an interval that we use the whole thing for. That's the beginning of that current interval or the partial interval at the end. So we'd only really need these first 4. But each of these could be computed by, well, substituting in 0 for a, and delta x was this, also stated above. Delta x is 0.3. So if I have 0, 0 plus 0.3, 0 times 2 plus 2 times 0.3, 0 plus 3 times 0.3, and if you were a computer, you wouldn't think that was a weird thing to say, but as a human, you're like, oh, I'm just going to count by 0.3s. So 0, 0.3, 0.6, 0.9, or increasing by 0.3 each time. In other situations, if we're not starting at 0, those don't have to be multiples of delta x, but since a is 0 here, this is the same as just, well, 0, obviously. This would be the same as just delta x, 2 delta x, and 3 delta x, obviously, since a is 0. But if it's not, you get these other numbers. However, the distance between them is equal, because we have equal lengths for our intervals. They're all delta x units long. All right, so if you're a computer, we did this in approximately, milliseconds of milliseconds. Millions of milliseconds. But now we need to find the rate values at each of those. So r of this column. So I need to find r of 0, r of 0.3, r of 0.6, and r of 0.9. Now, I'm just going to do this by estimating visually, because I don't want this to just be a symbolic exercise, but get some numbers out of this. But looking at, let's see, I'm going to scroll back for a moment, and all this writing is going to be on top of itself. But in the picture, those rates at 0 looks to be about 0.25. At 0.3, it's about 1. So I'm going to write this next to it because I know where r of 0 is about 0.25, which means 25 pounds per second. R of, let's see, 0.3, it looks like about 1. So just estimating visually. And this is 100 pounds per second then. R of 0.6 looks like about 3, meaning 300 pounds per second. And R of 0.9 is just to the left of this peak, looks to be 1 notch below 5, so I'll call it 4.75. Since there's 4 tick marks per interval here. All right, so scrolling this back up so that this goes back into my chart. Magic writing. All of these then are rates, measured in hundreds of pounds per second. So 0.25, 100 pounds per second, 100 pounds per second, 300 pounds per second, 4.75, 100 pounds per second, meaning 475 pounds per second. And then, well, this expression here, all this is just, again, order of operations, one more thing tacked on, this extra times delta x. So I've got a rate times an amount of the width of this interval, an amount of time. Now, rate times time sounds like distance, but it's not traveling rate, it's a adding weight rate. But this is our MDX sort of expression. So this indicates a change in or a variation in the weight of the sand on scale. So this is an accumulated weight during this interval, which if I'm using a rate of 0.25 times this interval, 0.3 seconds. So adding 25 pounds per second for 0.3 seconds. Let's see, 0.25 times 0.3 would be 0.075, if I'm doing math right. Decimal, yeah. So this is how much accumulates. This would be that many pounds, well, hundreds of pounds, so 7.5 pounds. So if I have 0.3 seconds at 25 pounds per second, you can see that, oh yeah, 0.75 or 7.5 pounds, which is 0.075 100 pounds. Weird way to do this, but it's just our rate times the amount of time that we're using that rate. So the rate at which the weight is accumulating, the rate at which the sand's being dumped onto the scale, times how much time I do it at that rate. Gives me a little bit of weight. Now, in the next interval, I'm not going to pay attention to this number. I'm just going to use my new rate, 1, meaning 100 pounds per second, times 0.3. So this is 0.3 100 pounds, meaning 30 pounds, if you want to translate it into non-computer sounding language. This is 0.25 times 0.3, 1 times 0.3, faster rate, 300 pounds per second for 0.3 seconds, gives us 0.900 pounds, otherwise known as 90 pounds. And on our fourth interval, we need 4.75 times 0.3. And let's see, 12, 13 and a half, 14, let's see, 1.425, I think. So meaning 142 and a half pounds. So this is just, if you're a computer, this takes like, zip, instant, you're done. You just did like a few multiplications and evaluating functions. Evaluating functions is actually one of the harder things for computers to do. But in any case, work-wise, this is a pretty simple function. So in any case, our 3 rows, then, these are x values. These are the rates at those x values. This is accumulation during the intervals at which those x values were the beginning. So if I want to take a look at, well, how much then accumulated during all of those 4 full intervals, that's just add up those 4 numbers. And there's a line at the bottom of this chart to add up those 4 numbers, and I don't really know what this adds up to. Oh, wait, I do. I have it on a different sheet. I'm going to skip the doing more computations by hand and testing my arithmetic skills in lieu of, I'm going to click over here. So I type this out. There we go. So we've got those 4, and then the current interval, the one that x is in the middle of, that's only 0.2 units long, x minus left of x, 1.4 minus 1.2, otherwise known as 0.2, the amount of time we use that last rate for. So I've got left of x is 1.2, r of x, when x is, and I didn't write this on there, when x is 1.4, this is looking for approximate rate at 1.4, which is the same as, to talk about what we were talking about earlier, r of left of 1.4, which would immediately translate to r of 1.2. Those are the same, because left of 1.4 means the left end of the interval, immediately to the left, the interval that is closest, starting to the left of 1.4, and this is also the same as r sub f, the exact rate function at 1.2, r sub f of left of 1.4. So r of 1.4 and r of 1.2 and r sub f of 1.2, the ones using left, all have the same value. It's slightly lower than this. That was that ending value on the graph, about 4.25. And so if we do this rate times the amount of time we use the rate for, we get this last numerical approximation, 0.85. Add all those together, all the stuff in gray, and it adds up to 3.475, meaning in the 1.4 seconds, approximately 347.5 pounds of sand were added to the scale, according to this approximation. Is it exact? No. If you look at the graph, let me just pull up the GC with this writing on it for a minute. You can see that I've got underestimate, 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 overestimate, overestimate. So it's not too bad of an estimate overall. Sometimes too high, sometimes too low from one interval to the next. But if you've got some too high and some too low, then I guess it's not that bad. Now, speaking of not that bad, that's all relative. But if I want to make a better estimate, as a person, that gets really annoying. That would be like, okay, make the intervals smaller so I have less error between where my approximate rate is and the actual rate. These rates would all be closer, but then I'd also have to do a heck of a lot of computations. This is at 0.08. How many different intervals between 0 and 1.4 if my intervals are 0.08 long? A lot. That would be really annoying to do by hand. However, a computer doesn't care. You can also see this is the same general shape here. I think we talked about this at the end of class on Thursday. This is the same general shape here as what we had with larger intervals. It's not as chunky looking. Let's see. When delta x is larger, you can kind of see the bends where we're changing from one rate to the other. When delta x is smaller, we're still doing that, but it's just like from a distance. Unless I were to zoom in really close, I'm not going to notice because these rates are pretty close together. And the smaller delta x gets, because this r function doesn't have any weird sharp corners to it where it changes all of a sudden and I can't help that, these constant rate approximations that I'm using are going to be closer and closer in value to one another, as well as position, closer and closer in value, y value to one another. And so the transition from one to the next isn't going to look abrupt in terms of how fast the sand's accumulating when this delta x gets smaller and smaller. So let me put this back to 0.3, or 0.3-ish. That's pretty close to 0.3. So this is when n, meaning my x value here, is at 1.4. So according to this graph, this should match up with what we just did on that worksheet. It came out to, what, 4.375 or something? 100 pounds of sand. That would indicate, if I look across here, okay, this is at 4.3 something. The height of this purple graph represents the weight that's accumulated between time 0 and 1.4 cumulatively, like all of that, not the separate values of it. The separate values you could find by looking straight across from whatever point you're interested in. But the y values here represent the cumulative weight of sand that's been put onto the scale since time 0. So right now it's a little bit over 4. That matches up with that 4.3 we had. If I make my delta x intervals smaller, maybe this looks a little bit higher. It's not too far off though. It's pretty similar. So maybe it looks like 4.5, meaning 450 pounds of sand. Now, clearly if I were trying to do something with the sand in specific, I'd want to be more precise than, it's off by like 20 or 30 pounds, no big deal. Probably would be a big deal. But this is still just using an approximation. It's just using an approximation that, while tedious to do by hand, is just as easy for a computer to do if you set it up. It's not any magic. It's just more math than humans like to do in a reasonable amount of time. See if it'll let me click on it. No. All right, so ooh, didn't mean to do that. There we go. All right, so what I was trying to do is, so when I had this delta x extremely small, and I just have this going on farther than what it was before. When I have this delta x extremely small, this looks just like it did before, only it just extends farther. Now if I make delta x larger, back to where it was before, around 0.3, what you're seeing here is a comparison of what happens when delta x is largish, the purple, and when delta x is small, the black. So you can see they're pretty close together. They're definitely the same type of shape, goes up and over, meaning increasing weight first slowly, then more quickly, and then slowly again. But you can also see as this delta x gets smaller, this purple curve gets closer and closer to what I had before this black. Now what I actually have as the black curve there is not really an approximation. I mean, in a sense it is, but what I did to get that black curve there is using the notation that means don't do this just for delta x equals 0.09 or 0.009 or 0.00009. Like, imagine delta x becoming infinitesimally small. It can't be 0, because then nothing would happen. We'd never progress from one interval to the next. But just imagine thinking back to the beginning of the semester and the random assignment. You're like, how does this relate to what we're talking about in class? Ants and carrying grains of sand and filling the Grand Canyon with sand. Or no, the ants were running across the country. The Grand Canyon was being filled with sand. As long as sand actually has some amount of volume to it, no matter how small it is compared to the overall goal, if you put enough of it in there, you can eventually fill the Grand Canyon. Now, if I have delta x as 0.0000000 whatever, eventually I can progress forward as far as I want by adding little bits of x at a time and doing little tiny bits of accumulation at a time. It has to be greater than 0. If I had 0 volume sand, it would never fill the Grand Canyon. If I have 0 with delta x, it will never go anywhere. But if I just imagine infinitesimally small or exceedingly small, like as small as you can imagine, eventually, if we put together enough of them, we'll progress forward. And there's a different notation for this because we don't actually want to try to count, well, how many of those are there? Essentially what we want is the idea of, instead of using like 5 intervals or 6 intervals that are all like, moderately small width, or maybe 100 intervals that are pretty small, I want to imagine like using all of the different rate values as if points were grains of sand next to one another, and I'm going to use the rate value from every single grain of sand laying out on the rate curve So every single one of those I'm going to use for a little tiny bit of time and add up all of the rate values and use them all for a little tiny bit of time. That's what I get when I have this nice smooth looking curve here, because again, it's kind of pieced together one little grain of sand at different angles at a time, if you want to imagine that. So this idea of, as long as something isn't 0 in size, I can make it as small as I want and something can be accomplished. And what we use a different notation for that, just because we don't want to list the how many intervals are there part. And also, if my intervals are exceedingly small, I don't know if you can imagine being in the middle of an incomplete interval that's as small as you can imagine, but that wouldn't really make sense. Even this current interval would really be the same size. So although this isn't actually part of what we're doing on your tests, there's just like, I just want to show you the notation of the progression, and this is kind of looking forward to what we're going to be doing a week from today. Although we're going to do more with it a week from today, and over the weekend you'll be reading about this. But let's see. Where am I? So, kind of recappy stuff. What we've been working on is the second of these two fundamental calculus problems. You know how fast a quantity is changing at every moment, and you want to know how much of it you have at every moment. Or at least you want to know how much of it is accumulated relative to some starting point at any moment past that. So the first problem here, we'll get to this later. The first part here is called differential calculus. We'll do that next. The algebra for it is much less tedious than we just went through, but the meaning for it comes from what we just did. That's why we're doing it second. What we've been working on is typically called integral calculus, and just like in English, like differential, differentiating or separating out into different pieces, and integral, like integrating, is putting together into one big piece or accumulating. Those words are opposites. These are opposite sorts of processes. But the second task here in this order is what we've been working on so far. And we've talked about, okay, if I know how fast a quantity is changing, if I know a rate, what happens because of that rate? Or how much do I have, including maybe a starting value, maybe not, because of that rate? So what we did is we started at an exact rate of change function, and to progress from there, to start figuring out how much of something we have, we used our tools of constant rate of change, which constant rate of change would be easy. Unfortunately, most things don't change at constant rates all the time for all independent quantities. So I want to know an exact accumulation function. That's actually an ultimate goal, but all the work is in the in-between steps. This exact accumulation function is, well, it's just like rewriting something with different notation. It's not actually doing additional work or building additional concepts other than just the idea of, like I said, instead of 0.3 for delta x, like grain of sand width for delta x. So what we did was use constant rates for smallish intervals. If we make them smaller, we get better approximations. And use the rate at the left end of intervals. You could also do this at the right end of intervals. It doesn't make any difference. We've just used left instead of right, because you can pick either one and it works out the same. When you have extremely small intervals, the rate value at the left and the right of the interval are going to be approximately the same. So in any case, once we figured out how we wanted to set up our approximate rates, and I just have the large intervals shown here so for easy to see, we summed up all the changes based on those. So here's our m values that we're going to use. Here's all the mdx's for a whole bunch of different values of m. We're going to add them all together. And we had, you know, like a little extra current interval, which is really another mdx term that's just structurally a little different, but it's still adding up a bunch of rates times change in the independent quantity, change in x. And we end up with this approximate accumulation. So getting from exact rate to approximate rate involves setting up the whole problem. Where do I want to start from? How wide do I want to make my intervals? And then, okay, I'm going to use the left end of each interval's exact rate as my constant rate for the full interval. But once you do that, then it's just a matter of, oh, m dx, m2 times dx, m3 times dx, m4 times dx, and add those on as you go. So the farther your x is from that starting value, lowercase a, the more stuff you will have added together to get to your current value of this plain capital A here, this approximate rate, or the approximate accumulation function. So if we make delta x small, then we get this idea of an exact accumulation function. Exactly how much has happened because of the rate, by using not just like 3 or 4 or 5 different rates from the curve, but the idea of every single rate, every single point on that rate curve has been used for a little tiny infinitesimal amount of time, dx in general. Then we have this idea of, well, I have this rate function, I've used all of its values. I have this accumulation that comes from using all of the values, so it must be exact, or as exact as matters if you want to use slightly larger delta x. But to get from one to the other, if you just want to write that, if you're not concerned about, well, how am I setting this up and how am I doing the approximation, just to write that you're doing all of this and making delta x extremely small so that we don't want to write all this summation and count the intervals and all that. Just say, oh, I want exact accumulation due to this rate r sub f. It's called an integral. Like I said, this is called integral calculus. That just means we're combining everything together and taking all of its rates to generate everything that's happened accumulation-wise. It could be negative rates, so de-accumulation, but we're putting all of it together, integrating everything. It's called an integral. And there's a different notation for it. It doesn't tell you what to do. The sum notation actually tells us what we're doing. This is just a notation that indicates, well, what's happening. So this looks a little crazy. I want to explain what the parts of this are, just so you can, because I'm going to ask you to read this over the weekend. But my exact accumulation function, a sub f of x, is given by, so there's this symbol here, this kind of squiggly line. What that is, it came from a stylized Germanic S for sum, just like we used the Greek sigma for sum when we had delta x size intervals. This is if we have infinitesimally small intervals, or imagining using all of the values of r sub f. And in fact, what this notation means, I have r sub f. Now, there's this mystery t here. T isn't any of the axes on here. T is an extra variable that we're using. And what happens is we let t take on all the values from a through x. So it kind of plays the same role as j in the summation did. It tells you how to get all of the different rate values. But instead of having just interval numbers like j equals 1, 2, 3, 4, 5, I let t take on all the real number values, infinitely many of them, between a and any value of x that I want. So if it was 0 through 1.4 in those two spots, that would be a sub f of 1.4. And then I have the, whatever that weird function that I had on GC would be written in this spot. But this is a rate times a change in its variable. So as I let t vary a little tiny bit, so t takes on every little grain of sand value, and then dt is this width of a grain of sand, if you want to picture it that way. So every single x value between a and whatever I want this to be. So this is a function written like this. If I want it to be a numerical value, I'd put a number here in function notation, and I'd put a number up at the top. This a is however you want to define your accumulation. Where am I going to start accumulating? Time 0, time whatever else in a different situation. But in this specific picture, we were using accumulation starting at 0, so this would be 0 through x, r sub f of t dt. So t takes on all the values of a through x, or all the values of 0 through x, or it measures net accumulation. And these have the same kind of ingredients in their expressions, just the top one has a lot, like that's the computation that actually goes into this. But this short notation for exact accumulation eliminates a couple of things. One, it eliminates this counting how many intervals there are. So we're not going to count how many real numbers there are between 0 and 1.4. There's infinitely many. I just want to use all of those numbers. So there's none of this counting how many intervals and adding them all up separately, but that's really what this is doing. This notation is saying add up all of them. And there's also no distinction between partial interval and complete interval because, well, if they're infinitesimally small, you can't really have part of that because part of something that's as small as you can imagine would be too small. Kind of like, if you imagine something infinitely large, something head towards infinity. Well, what's bigger than that? Well, nothing because it's already infinity. So I can't have smaller than infinitesimally small. So I'm not going to worry about this part. I'm going to think about it as being a part of that same sum, or it's included in here. So that last partial interval would be the same size as every other interval. There's no smaller than smallest. So these have the same things, but the difference is what they mean. So this is knowing that we're doing an approximation, and it tells us what sort of approximation we're doing, where we're starting, and more importantly, what's delta x. This is to do an exact computation, and all it is the same thing, but making delta x exceedingly small. It doesn't have any notation to indicate that, but this is the short notation just to indicate exact value of accumulation. So you can read that, like kind of interpreting it instead of just reading the symbols. I'll tell you how to read the symbols too, but if you want to read this with meaning for it, this a sub f of x is the accumulation in f. So a sub f, accumulation in f. F would be like the total weight, including anything that was there on the scale to start with. A sub f is just what happens because of this rate. So the accumulation of changes in f, due to its changing at a rate of r sub f of t, at every moment t from a through x. So if you wanted a numerical value, then an exact amount of accumulation, a sub f of 7 or something like that. You can say, oh, it's the accumulation in f due to changing at the rate r sub f of t at every moment from a, 0, through 7. And using every single value, all infinitely many of them, of the rate between time 0 and time 7. So this doesn't tell you what to do. It just expresses the idea of what was above, but exact. So there's not any additional like, oh, well, this is our end result, magic, now we're done. It doesn't tell us what to do. It's just a way to write it that doesn't involve an approximation with a certain number of intervals and delta x's and stuff. So just comparing these, they have the same ingredients. They have a rate, an m times a dx, a rate times the amount of time I use the rate for. And I have a starting point and a finishing point. A and, well, it could be a number, or it could just be x to be a function. So I can imagine it growing as x changes. But just this whole f here. The one thing I did want to point out that for either one of these, this f is kind of mystery. This just tells me, and I could have an approximate with this also. If I wanted a total amount of something, like how much sand altogether is there on the scale by time 1.4, not just how much accumulated between time 0 and 1.4. I'd have to know how much was on there at the beginning, at time 0. If there was any, if there wasn't any, maybe there wasn't, maybe there was. But I'd have to know that. So if the scale already had p 100 pounds of sand on it, if you remember our units were hundreds of pounds, function f, the thing that has been accumulating, would just be the same exact, it's this p plus whatever we had before. And we could use the exact or we could use the approximate, but just that starting amount plus what accumulates afterward. Y initial plus mdx. So again, I wrote the short one here so that it's an exact total amount function. If I wanted to have an approximate total amount, I would just put the summation here instead of this integral sign. It's still just add the starting amount, that y initial plus what happens because of the rate. So if you are looking for not just the new accumulation, but the total overall amount of something, whether it's total distance from school or total number of people in a room, as opposed to just how many more people or how many more miles were driven, we have to have some sort of starting amount. That's what this p or whatever sort of y initial, some original value of the dependent value of a is also the dependent value of f. Some original value for that at whenever we started measuring accumulation, which in this case was time 0, based on the problem we were working on before. But just so that's not this mystery, like, well, what was f? Because we had a rate of change of f, and then we ended up with not f, we ended up with something else. The difference between f, the amount of something, and a sub f, the exact accumulation of that something, is just the only difference is a starting value when we started measuring accumulation. So this could also be written as a sub f of lowercase a sub f of 0 in the context of this problem, the amount that we had at the beginning before this accumulation started happening. So this is just what I was saying before. This short notation is very nice to write, and when people want an exact value, they write this sort of thing. They don't bother writing out this whole big thing and then say, oh, and imagine delta x is really small, because as you know, this is really tedious. It's a little dizzying to look at, the big summation form. So it really means the same thing. So it's got the same ingredients to it. We've just got an infinitesimally small value of delta x, so that we're using all of the rate values, and there's not really any current interval versus completed interval. Wherever the current interval is, it's the same size, infinitesimally small, as the complete intervals, so we don't have to worry about that extra term. And if we just compare these two expressions, sorry, that's just a little dot left over from not scooting something quite right. If we look at these, they have the same sorts of parts to them, just what I was saying before. So think about that sentence that I had about fundamental problem of calculus. We know how fast something's changing, and we want to know how much of it we have at any moment. And we find that by summing up little bits of accumulation that happen at varying rates from some starting position that we define as a part of our question through either a general value of x or through a particular value of x to get a numerical result. But if I want to talk about like this, we know how fast something's changing. Oh, that's the rate. We know a rate. So that rate in our summation was expressed as this r, or we could use r sub f here also. But in this summation, these are just the left ends of intervals. Here I can use r sub f of t, r sub f of whatever this is inside. I'm going to have all the different values because, well, every interval is essentially one value, its whole like little neighborhood around them so that they're packed together. But we want to know how much we get out of that. So we take all of our accumulation, add it together, and so forth. But this end result is the how much of something we've accumulated, whether it's exact or approximate. So we start from a rate function. We want to know an accumulation function is the kind of brief way to say 1 and 2. But we find that either in exact or approximate form by summing up Germanic S up there, Greek S down below, sum up a bunch of stuff. What are we summing up? Accumulation, MDXs. All right? So in this one, it looks nice and short. In this one, a little bit more tedious because we have to define these to be the left endpoints of intervals of with delta x starting at a. In this one, we don't worry about the a until the end. But each of these is a rate times the amount of time we use it for, the amount of independent variable we use it for. It doesn't have to be time. A rate times how much we use it for. The starting value of x is indicated in both of these, x minus a over delta x. You see that in here. That tells you where we're starting measuring accumulation. And this a, this is like the lower end of the interval, the lower end of our, the start of where we're using our rate. So it's at the bottom. And then up through, well, a current value of x, and it could be just a symbol x to be used for a function you can sub in later, or you could put in a numerical value in these spots. So if I wanted to find a value that value would show up inside the parentheses in function notation on the left. If I want to find accumulation by time 1.4, I'd put 1.4s there, but then I'd also write it inside the notation. 1.4 would go here or there. Those are the only just plain x's we have. Only way to tell like an end point. So these last two here, this 7 and 8 that I have, just says what's the independent variable of each function and what does it mean? Well, it's the same thing in both functions, right? They're both something of x. Well, in the context that we were just talking about, that was time in seconds since we started pouring the sand onto the scale. But it's x in either case, right? And this indicates whatever x's value is. I can measure it relative to a, say how much x has changed, or how much that independent quantity has changed since time a. Or I could just, each point has its own value, like maybe it's just a time of day, something's, you know, time of day measured in minutes since noon. So if it's 12:07 p.m., just past noon. But that independent quantity is x, and it shows up, again, only in two spots in the function notation, and then on the right-hand side at the top, the end, the upper limit of the interval. And again, up here, we have x minus a, the end and the beginning of where we're making our intervals when we set them up to be delta x wide. So this last question here, what's the dependent variable of each function? And what does it mean? Well, the dependent variable is the entire, you know, we can call it a sub f of x or a of x. In context, maybe use that accumulated weight of sand approximate or accumulated weight of sand exact. But again, this short notation up above, it's not doing something else, and there's not anything else that we're going to do with it right now until we figure out how to do the other fundamental problem of calculus. All that we're going to be doing for right now is just looking at it and saying, oh, well, that looks weird. It's a lot shorter, it's nicer to write, but it doesn't really tell us all that's going on. It doesn't tell us the story behind all this. This is just the way that we would write exact accumulation, as opposed to trying to alter this sum to make it better and then say like, and delta x is really small. Instead of writing all of it, then we just do this. So with delta x not exceedingly small, just realistically small, you could do some computations manually, like we did on the sand worksheet. With it a little bit too small and a little bit tedious, you can use a GC file to compute whatever you want as an approximate rate. And you can even make delta x smaller and smaller, so it gets closer and closer to exact. But this symbol here, this integral sign, this is actually built in as a function in GC. So you can compare values between exact and approximate accumulations that you get, these net accumulations, using delta x's of various sizes. And that's what that in Canvas, let's see if I have this pulled up. Oh no, licensing your dog. Cool, I have to do that today. Let's see. Well, maybe I won't do it right now because I don't feel like trying to log in and having my cell phone help me out. But on Canvas, there's a link to a GC file that says use as you wish. It has the sum programmed in there, and it has a way for you to alter the delta x. It's kind of like what you see up at the top of this file. This just has some like teacher stuff programmed into it, but we've got a rate function and a delta x and graphs, and you can also see values of by clicking on the graphs. Approximate accumulation and exact accumulation. What's different in the GC files, it gives you also a way to see near the top instead of I'll scroll down here. Let's see, where is it? This is all the programming up behind making that look cool. Looks pretty ugly, right? Where is it? It's the last one. So, in order for this to work, you have to define all the functions you're going to use, including left. Left isn't a built-in function. So here's that a plus x minus a over delta x, delta x. This is just something to make the graphs turn out without any random extra lines in it. here's this summation. This capital R was used as the name of the rate function up at the very top, but this looks familiar, right? This rate function evaluated a plus j minus 1 delta x times delta x from j equals 1 through, that's exactly what's programmed in here. So that's where this a of x comes from. When delta x gets too small, this one's used instead because otherwise the calculator goes, the GC goes a little bit crazy. But here's this integral notation. The integral of this rate function from 0 through x at the current value apparently is 3.2, wherever I happen to be stopped at. Oh, that's f of 1, sorry. But this integral sign is built in. You don't have to define that or type it all out by hand. There's no defining what delta x is. You just have to use some other letter, and GC doesn't like the letter t, because whenever you type t's, it tries to graph in some other called parametric form. So just use something else other than the t that I had there. But you can see, oh, well, this is that integral something. That's what this black curve is here, actually. It's that integral thing being graphed from 0 through any value of x, where x is controlled by this. So here's that big capital R. It's that lovely rate function. You have something, like I said, kind of similar to this, but without all the nonsense teacher stuff in it, so that you can see approximate and exact accumulations and see them compared and set your delta x to be what you want. Play around with it if you want. Think about what the pieces mean. But I'm going to stop at that for today. We've got a test on Thursday. Hold on. The test is multiple choice and it's on Scantron. So make sure you bring a pencil so you can bubble in the Scantron form. Also bring or know your student ID number, because you're going to put that on your Scantron form also. Just name, student ID number. I hope you know your name. Student ID number, maybe not as much. And a pencil. So no calculators. It's not computational in nature. So yeah.
What do you recommend us study and look over to help prepare for the exam?
Everything, but I posted a bunch of stuff on Canvas. So there's
Okay.
there's a list of topics. There's a review session tonight. Wednesday? I forget. It's in an announcement. I forgot what day it is.
Yes.
Today, like 3 to 5 or something? Okay. Yeah, so there's a review session. There's some practice questions in Canvas, like multiple choice sorts of questions, matching true and false, ones that you can know right away whether you got them right or wrong.
Okay, thank you.
All right. Yeah, and don't forget, there is going to be a quiz that's about your summation that's only open tomorrow. It's in iMath.
The Scantron form will be provided, or do we have to pick one?
I'll provide it.
Okay.
Yeah. I'll bring the Scantrons.